quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves. When the peaks of two waves overlap, it creates a band of light. When the peak of one wave meets the valley of another, light is canceled out. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. It's been called the granddaddy of all quantum weirdness. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Welcome back, guys. It's lesson 36. We're coming down to the final stretch. Just a few lessons left. This is the first of a three-part set of lessons about the standard model of particle physics and quantum field theory. Now, you can't do all of the standard model and quantum field theory in 3 lessons, and maybe I'm foolish to try, but I mostly just wanted to give you guys a sense of what it's about. So that's what we're going to talk about. Let's get started. First of all, there are 2 major families in the standard model. There's the sort of matter part, which consists of the fermions, which is, and there are 2 groups of fermions, the quarks, up and down, charm and strange, and top and bottom. They come in pairs. Each pair has a positive and negative member. The positive is plus 2/3 charge, the negative is minus 1/3 charge. And notice that the positive charges are 1 elementary charge greater in charge than the negative charges. So the difference in charge between up and down is 1. And that's also true of the leptons. The leptons have a difference in charge of 1, but in this case, the electron has a negative charge. The neutrino, the electron neutrino, has a 0 charge, and so they have a difference in charge of 1 unit. Same with the muon and the muon neutrino, and the tau and the tau neutrino. So the leptons are relatively light particles with nearly massless partner particles. The electron has much, much greater mass than the electron neutrino. But having said that, the up and down quarks are even more massive than the leptons. Then the leptons in the same column, I should say. And then there are the bosons. The bosons generally play the role of the force carriers that act between the leptons. I say generally because there are exceptions to that, but we got the gluons. The gluons, it turns out, carry the color force. In other words, quarks have a color charge, and the gluons are the ones that the quarks exchange with one another in order to interact via the color force. And the anything with charge and weak charge can interact using photons, which are the gammas, and then the W and Z bosons are the carriers of the weak force, and they interact with objects that have weak charge. And finally, I don't want to call the Higgs a force exactly. The Higgs is basically a field that is theoretically permeates all of space, and it enables these particles to have mass to the degree that they interact with the Higgs field. And we're not going to talk about the Higgs field today at all. I'm hoping that on the 3rd day of this, we'll have a chance to discuss exactly what the Higgs mechanism is and what the Higgs boson actually does. But let's start with the more straightforward and more direct interactions, and those start with the photons. So photons interact with anything that has electric charge. So that could be any of the leptons, any of the quarks. Those are the only things that have electric charge. And basically, the most fundamental interaction is simply an emission or absorption of a photon by an object with charge. So that's all there is to it. Then the weak bosons are the W plus, the W minus, and the Z, and they interact in a similar fashion to anything with weak charge. So, in fact, it turns out the electric and weak forces have been unified theoretically at high energy. They behave the same at high energy, but there is what you call a symmetry breaking that happens, and at the energies that we see on a day-to-day basis or in our laboratories, they appear to be very different. But in fact, the underlying theory is unified at this point. Then there are the gluons, which interact with quarks. So quarks carry color, and the gluons, in the same way that the photon interacts with the electric charge, the gluons interact with the color charge. And the other thing is the gluons actually carry color with them, and so unlike photons, gluons can interact with one another, and that's one of the things that makes dealing with the quarks and the gluons and the color force in general so complicated. Now, where can you go to learn more? There is a free book on the internet. You can go and grab it from the Particle Data Group, and it has all kinds of lovely details about all the wonderful stuff that you can learn about the standard model and how it all goes. I just want to point out a couple things. This is a free download, so it's an amazing resource. One is that we're going to be working with the baryons a lot right away, and I just want to point out also that these guys have a whole chapter set aside for Monte Carlo techniques, so I'm not making this stuff up. People really use this to get work done, and so as I'm encouraging you to use Monte Carlo techniques in your computing projects, understand that it's a skill that may prove useful in the future. Okay, so let's get back to those baryons. Why do we have this quark model? Well, part of the reason is, before the quark model, there were lots and lots and lots of different kinds of particles, and there were some relationships that people understood, but basically it was a zoo of many, many kinds of particles. And we understand today that those complicated particles are actually just superpositions, combinations essentially, of the 6 quarks that have been discovered. And so here's a couple of families you can see made up of up, down, and strange, charm, and so on. This is not a complete set, but it just gives you an idea of the complexity of particle physics, and when you actually go to measure these guys, how complicated it can get to understand what's going on. But anyway, let's start at the beginning. Let's talk about some simple processes that we might want to understand. So, for example, electron-electron scattering. What's the simplest thing that can happen? Well, one electron can emit a photon, another electron can absorb the photon, and that corresponds to a process whereby 2 electrons interact with each other. Of course, you could draw the same diagram for the hydrogen atom, because you've got a proton which has a charge, and the force between the proton and the electron can be thought of, at least at some level, as a scattering event of a photon between the electron and the proton. But that ain't all that can happen, because you could have 2 photons. And you could have 2 photons, and in the middle you could create an electron-positron pair and exchange those between the 2 photons. And so you can see that the thing can get fairly complicated. And part of the trouble with doing calculations in particle physics is that oftentimes you end up having to perform these calculations that include very complicated effects. And so that's what I basically want to introduce you guys to, is how you think about this stuff and how it goes. We're not going to get into too much of the thick of it, but you get an idea. So there's also, in addition to scattering, you can have decay type events. So for example, a Z0 can decay into two particles. And I want to point out the arrows here. We're thinking of time advancing to the right, and in this picture you'll notice there's an F advancing to the right. That's a fermion of some kind advancing to the right, but then there's an arrow that looks like it's going backwards, pointing back in time. That's an antifermion. So this would be a fermion and an antifermion, and they're not necessarily the same fermion, but the point is, when you have an arrow that goes backwards in time, that's a clue that that's an antiparticle. So here's something that does happen. We have a down quark with a charge of -1/3. It's going to emit a W minus. Now it turns out when a particle emits a W minus, it also changes its flavor, its character. And so in this case, the down quark is going to convert to an up quark. Notice the charge is conserved because on the way in we have a -1/3 charge, and on the way out we have a up quark with a charge of +2/3, and we have a W minus with a charge of -1. But then in addition to that, the W minus then decays into an electron, but it also has to change flavor, so we have a electron antineutrino. Now, if the neutrino were going forward in time, if this were a weak scattering event where you send in a down quark and an electron neutrino, you could scatter and send out an electron and an up quark. But this is a scattering event turned on its side in the sense because both the electron and the neutrino are moving forward in time, and so that means that's got to be an antineutrino because the vertex has to have an incoming and an outgoing particle, but the incoming particle is actually a decay product of the W minus. So anyway, I hope that's not too confusing. It's a little strange, I appreciate. And here's another kind of thing that can happen. You can have a positron and an electron scatter two gammas, but notice it would look like a scattering event if the thing were sideways. It would look like an electron scattering two gammas and then going off in the forward direction. But because we have the electron leaving the thing moving backwards in time, it's actually a positron coming in. And what we really have is a positron-electron annihilation producing two gammas. And here's another case. We have an up quark scattering, emitting a W plus and scattering a D. It's a D anti quark, right? But here's the thing. The D quark is moving backwards in time. That means it's got to be an anti-quark. And so what we really have is an up-down bar, which is a flavor of pion. It's a pi plus, basically. And so we have a pion decaying to a W plus, and then that's further decaying into a anti-muon and a muon neutrino. Notice the muon is moving backwards in time. That makes it an anti-muon, and it's decaying along with its associated neutrino. So that's the idea. Notice that the weak bosons are interesting, the W plus, W minus, because they change flavors of particles. They change electrons into neutrinos. They change up quarks into down quarks. They can even change an up quark, for example, into a strange quark. So, and here's an example of that. Here we have a strange quark changing into an up quark, okay, emitting a W minus, and then the W minus decays into a pi minus, a down quark and an up bar. So there's another example of something crazy that can happen, and you get the idea. I hope you get the idea. Let's talk about the basics of field theory. So the notion is in regular old quantum mechanics, we have T as a parameter, R is an operator, it's an observable, psi is a wave function, it's the state vector. Okay? We're going to change our point of view and switch to field theory. And one of the things that has to happen in field theory is R and T have to get put on the same footing. Now, there are some approaches that make T into an operator, But the approach we're going to take is the more common approach, is that in which we move r to be just a different parameter. So r and t are now going to become parameters, and psi is going to be elevated to an operator, and the state is going to be a ket, which tells you how many particles are in the various single particle wave function states, wave function type states that we can understand. And so it becomes a vector, the state vector. Okay, and what is the vacuum? The vacuum is just nothing. It's there are no particles in any states, and because nobody wants to write a bunch of zeros, we just use the zero ket to mean the vacuum. Notice that's different than the null ket. That is a real ket. It's just a ket with no particles in any of the states. And then you can think of a ket with a single particle in a particular momentum state as what you get when you apply a creation operator associated with that momentum to the vacuum. So applying a creation operator to the vacuum puts a particle in a particular state, and if you put particle I in state k sub I and particle j in state k sub j, you can do that with two creation operators. Now, depending on whether the particles are bosons or fermions, we may have different commutation relations for the creation operators. If they're bosons, then the order doesn't matter. You can put them in any order, but if they're fermions, then switching the order has to switch the sign in order to satisfy the symmetry requirements of fermions. So we'll run into that a little bit later, but I just wanted you to make sure you understood that the commutation relationship for bosonic creation operators is that they commute. For fermionic operators, I'll get there, they anti-commute. So what that means is if you apply them in one order and then you add to that what you get when you apply them in the different order, that gives you 0. Whereas for bosons, if you apply them in one order and subtract what you get when you apply them in the opposite order, that gives you a 0. So bosonic creation operators commute, bosonic annihilation operators commute, and the creation and annihilation operators commute with each other so long as they're talking about different momentum states. If they're the same momentum states, then the commutator is 1, and that's how you get the raising and lowering business. But for fermions, it's exactly the same creation and annihilation commutation relations, except that they're anti-commutators instead of commutators. So they anti-commute. Let's talk about a change of basis. The basis I've been thinking about as we've been talking about these creation and annihilation operators is the sort of the plane wave basis. If you imagine plane waves of fermion particles propagating through a big box of volume V, that would be the e to the ikr sort of version. But I want to imagine that we do a change of basis where we switch from the momentum basis to the space basis. So for example, if you have a state phi and you want to express it in the momentum basis, you simply use the identity, just like we've been using all year. But let's suppose you have a state x and you want to express it in the momentum basis. You would again use the identity, just like this. But x may correspond to a state of well-defined position, and we know what the amplitude is. If I have a state of well-defined position and I ask what's the inner product of the momentum k sub I, we know that that is going to end up looking like e to the minus I k sub I times x. That's just the definition of what I mean by a definite momentum and what it means to have an amplitude to have a definite momentum. I can put that in as k sub I on x, and I can get an expression that tells me how to write down the ket that corresponds to a particle at a definite position in the basis of plane wave momentum eigenstates. So we're going to use that. In fact, how do I get a particle at position x while I apply the creation operator that creates a particle at position x to the vacuum. But you can see here now I can read off exactly how to do that. What I do is I create a bunch of a superposition of different momentum eigenstates and have that act on the vacuum. But if I've got the vacuum on the right of the left-hand side of the expression and I got the vacuum on the right of the right-hand side of the expression, I can just get rid of the vacuum if I don't need to put the vacuum in there, and I have now a definition of what I mean to create a particle at position x. If you need an operator that creates a particle at a particular place in space, this is how you do it. It's a superposition of plane wave momentum eigenstate creation operators. So that creates a particle at position x. So how can I describe an interaction then if I've got this mechanism that allows me to create particles? What I might do is say, well, let's say I've got, I want to describe a scattering process where a particle comes in with some initial momentum, it scatters and ends up in some final momentum. I could do that with an interaction Hamiltonian that destroys a particle with momentum k and creates a particle with momentum k sub l. I'm sorry, it destroys a particle with momentum k sub m, creates a particle with momentum k sub l, and you can see that that's going to describe a process, an interaction that takes particles out of one momentum state and sticks it into a different momentum state. Well, if I have a particle coming in with momentum k sub I can create that by applying a creation operator to the vacuum with momentum k sub I. And if I want to create a particle with momentum k sub f, again, I could do that with a creation operator. What that means is if I want to compute something like the amplitude of being in momentum k sub f after an interaction, starting with momentum k sub I end up with a sum that looks something like this. In other words, this gives me the matrix element between the incoming and outgoing wave, and I'll end up with a sum over the interaction potential and then these creation and annihilation operators acting. Notice that I only get something if the destruction, that A sub km and A dagger sub ki happen to line up, and equivalently with the second two have to line up. Let's think about another possible process we could imagine. Let's say we want to describe a decay at a definite place, but at an unknown time. You might imagine trying to compute Fermi's golden rule or something like that. You have Fermi's golden rule. It says that the probability of a decay goes something like the matrix element between the incoming and the outgoing situation. So I need that matrix element in order to compute the probability of a decay. But notice that if I have a definite place but an uncertain time, I have to express my psi and my psi dagger with some kind of superpositions of creation and destruction operators in the plane wave representation. And if I let x equals 0 and I go to do that calculation, my x is at a definite place, but I'm going to have to integrate over all possible times when this interaction could occur. And notice that the kx's are all going to go to 0 in that integral, but the omegas are still going to be there, even if I put in x equals 0. And so I'm going to end up with a factor in my calculation that looks like an integral over all possible times of e to the I omega sub L plus omega sub m minus omega sub k. They come right out of the definition of the interaction. And notice that that is nothing other than a delta function. It's a delta function that ensures that the energy is the same at the end of the scattering experiment as it was at the beginning. In other words, if I allow the time to be unknown, I have to integrate this process over all possible times when it could occur. That in itself is automatically going to ensure conservation of energy. Similarly, what if I have an interaction at a definite time but in an uncertain place? In a similar way, we're going to have to integrate over all the places where this could happen. But if I know when it happens, I can just put in t equals 0. And again, I'm going to end up with an integral, but this time it's going to be an integral of e to the I kl plus km minus kk. In other words, it'll be an integral that looks like a delta function, but it's a delta function that ensures conservation of momentum. So the moral is that if I have a process that I don't know where it's going to happen, when I'm done with the calculation, the total momentum of the system before and after is going to have to be conserved. And if I have a situation where I know neither when exactly it happens nor where exactly it happens, then the same process, I'm going to have to integrate over all possible times and all of space, the same exact process that describes the interaction in terms of these the plane wave representation is going to ensure that the momentum and the energy are both conserved. So that's an interesting insight. I just want to point that out to you, and we'll encounter this as we do other calculations. But what I really want to finish with today, I'm going to finish up here in a little bit, is to describe how forces come about in a field theory context. So you remember that we studied the simple harmonic oscillator, and I want you to imagine we have a field that can be thought of as having a position-like part and a momentum-like part. For example, this would be like the electric and magnetic field. The electric field is a little bit like position. You can formally identify magnetic field as a little bit like momentum, and you can write down a Hamiltonian that looks like the sum of the squares. Remember that the energy density of an electric field, electromagnetic field, goes like 1/2 epsilon 0 E squared plus 1/2 B squared over mu 0, and so that smells a little bit like a simple harmonic oscillator if you identify one as position and the other as momentum. The good news is if you can do that, then you can write out the Hamiltonian exactly analogously to the simple harmonic oscillator, and since we already know the solutions to the simple harmonic oscillator and we cooked up the creation and annihilation operators, we call them ladder operators or raising and lowering operators, but they're exactly the same thing. We cooked those up for the simple harmonic oscillator, and using those we could work backwards and solve for the position operator and the momentum operator in terms of the raising and lowering operators. We can do exactly the same thing with the field. Basically, what we get are in a box of volume V, we end up with these fields that look like the modes of the field in the box. And so we can write out, for every single mode, we can write out the plane wave representation of the field using the the creation and annihilation operators for the field. And the total Hamiltonian of the field just works out to be the sum of the energies in each of the modes. And each mode then acts like a simple harmonic oscillator. That's the idea. Very quickly, I want to suppose we want to model an interaction between two objects which interact with this field. So let's let the objects be the psi field, and the interaction, the things that mediate the interaction, we'll call that the phi field. But I don't want to really let the psi particles move around. So what I'm going to do is say, let's imagine that the psi particles are stuck at some particular place. So instead of psi dagger psi, which would sort of measure the number of psi particles at a particular place, I'm going to replace the psi dagger psi with just a delta function. That has the effect of saying, well, basically the psi particle is going to be stuck at R1. It's going to have an infinite mass, essentially, so it's not going to move around or do anything. But it's still going to interact with the phi field. So I'm going to forget about the psi field for the moment. I'm going to focus on the phi field, which would be the field of the bosons with which these phi particles interact. That's the idea. Now the delta function is in the Hamiltonian density. Hamiltonian density is a Hamiltonian operator per unit volume. So I need to integrate over all of space in order to compute anything like the Hamiltonian itself. And so we can integrate over all space, And what we get is a superposition of plane waves. But notice that because the delta function put the psi density at all focused in one place, R1, that this Hamiltonian now has a definite R1 in it in the plane wave representation. Now here's the question. I want to use perturbation theory to calculate the effect that being in this field of phi particles has on the psi particle. And so I could compute the perturbation. The first order perturbation of the energy is simply going to be the expectation value of the Hamiltonian in the unperturbed state. Well, the unperturbed state is the vacuum of the phi field. And so if I plug that in, notice that every single term has an A dagger and an A, but if I apply A to the vacuum, I get nothing. If I apply A dagger to the vacuum, I get one phonon, or one boson in the field. But notice I'm then taking the inner product with the vacuum, and I'll get nothing. So it turns out there is no first order perturbation. The question is, what happens if I calculate the second order perturbation? Remember how you do that is you take the sum of all the states except for the vacuum. You don't include the vacuum because we don't want to introduce a degeneracy here. And you compute the inner product between the vacuum and the kth mode, and then the kth mode back to the vacuum, and you divide by the difference in energy between the kth mode and the vacuum. That's the idea, and you see what you get. Now I want you to think about this. This is actually corresponds to an emission of a boson and the reabsorption of a boson. You can think of the 0h1k as the emission process, and then the kh10 as the absorption process. In other words, that's the amplitude to excite one boson through the interaction, and the amplitude to de-excite one boson, again through the interaction. That's what's in the numerator there. And you got to divide that, according to the rules of perturbation theory, by the difference in energy between the boson in the field and the vacuum. So let's think about that. If I calculate 0h1 on k, notice I just get I get a g squared, I get a 1 over v, and I get e to the ikr. Remember, e to the ikr1 was what was in those the coefficient of those creation and annihilation operators. And so I get something. I can add those guys up. The bad news is that when I go ahead and put in the density of states, remember that we're adding up all the k vectors, which means we're in k space. We're going to put in the density of states in k space. We're going to go ahead and put in the energy. And if you do all that, you end up with this terrible monstrosity. But the terrible thing, the truly terrible thing is, notice that when k becomes large, I get a k squared upstairs, and downstairs I use the relativistic energy formula for the energy squared. I get a k squared plus a constant. And so as k gets bigger and bigger, the k squared upstairs and the k squared downstairs will cancel, but it's an integral over all k, all the way out to infinity. And so the bad news is this integral diverges. It's infinity. So that's bad. I mean, it looks like perturbation theory might not have been such a good idea. But never mind that. Let's march ahead and see what happens if I put in two psi particles. In other words, I put in two delta functions. I put a delta function at R1, I put a delta function at R2, and I repeat that whole process. I mean, if the first one was infinity, then the second one's got to be infinity too, right? So this is hopeless. But let's try it. Again, there's no first order perturbation for the same reason as last time. But if I put in both of the interactions into the second order perturbation formula, notice that I get an interesting thing happening. I get when I multiply all those products out, I get the same thing I had before. I get the charge 1 interacting with itself. I get charge 2 interacting with itself. And remember, we already know that if we calculate the integral for a charge interacting with itself, we're going to get infinity. So this is not looking any better. Now we have 2 infinities. But these middle 2 terms are more interesting because notice what they represent is the vacuum interacts with the charge and puts a boson in the field. Then that boson in the field interacts with the other charge and goes back to the vacuum. So this corresponds to an emission and absorption of a boson by one and an absorption by the other. And the other term is the same thing, except it's the complex conjugate. Well, let's think about that. If we have Hi1 and Hi2 given as these expressions that we already worked out before, and we compute this inner product, notice that a dagger on the vacuum gives me 1, and 1 on 1 gives me 1. So this actually produces a non-zero result. A on the vacuum gives me nothing, so that doesn't contribute. But for the other inner product that I need to compute, I go 1, H12 on 0, and so starting with 1, it's the annihilation operator that produces something. It gives me the vacuum, and then the vacuum on vacuum gives me 1. And so in this case, it's the annihilation operator that contributes to the inner product. And when I multiply those two guys together, notice I'm going to get an e to the ik r2 minus e to the ik r1, or e to the ik r1 minus r2. The other term is exactly the same, except it's the complex conjugate. So what I'm going to wind up with is e to the ik r2 minus r1 plus e to the ik r1 minus r2. That's, of course, nothing other than the cosine of k r2 minus r1. And as you know, the 1 is from the it's from the two outer terms, which were the charges interacting with themselves, and that part gives us infinity. Still gives us infinity, twice as much infinity, in fact. But the second part is interesting. Let's go ahead and work that out. If we put in what k times r1 minus r2 is, let's imagine r1 minus r2 is just called r, and it points along the z-axis. Then k dot r is going to be kr cosine theta, where theta is the angle relative to the z-axis. And so I get this integral. This integral actually looks very much like the integral in Griffiths that he does to study the Born approximation in scattering. I'm going to repeat parts of it. I can separate the cosine into the e to the ikr cosine plus e to the minus ikr cosine. I can do the integral over sine theta, and that gives us a sine kr times k over the energy denominator. Again, the energy denominator I've converted to the relativistic expression for energy. And this can be done with a contour integral similar to the contour integral that Griffiths does, except this time there's no poles along the axis. The only poles are in the upper complex plane and the lower complex plane. This is what the integral reduces to. In the upper complex plane, there's a pole when k is equal to imc squared over h bar c. And in the lower complex plane, there's a pole when k is equal to minus imc squared over h bar c. But in both cases, we can evaluate the integral by using Cauchy's complex integral formula or whatever. We calculate 2 pi I times the residue at the pole. To find the residue, we simply plug in, we get rid of the pole part and we plug in the value of k in the rest of the expression. So downstairs we're going to get 2mc squared. Upstairs we're going to get imc squared over h bar c for k. And if you put that in, you get a real exponential, e to the minus mc squared r over h bar c times some junk out in front. You get the same result for both of these integrals. And so plugging that all back in and looking at, forget about the units, the units are whatever they have to be in order to make this thing work out to be energy. What I want to focus on is that the energy goes like minus the coupling constant squared divided by the distance between the two charges times an exponential factor that's related to the mass of the bosons. This is Yukawa's famous formula, and we worked it out for a simple kind of a field theory that has the simplest possible context, is just bosons with no polarization and no other special features. These are not photons, these are not mesons, because we haven't invoked any of the necessary technicalities in order to handle photons. Photons are, they've got polarization, and the charges are not electrons or quarks or anything, because those guys have other features as well, like spin and so on, that we haven't taken into account. But I just want to point out that this is the sort of mechanism through which a field theory can give you an attractive force. And the interesting thing is that if you let the mass of the bosons become 0, then this gives you a 1 over r potential. If the mass of the bosons is not 0, then this is the Yukawa potential. And in fact, you can see very easily here, h bar c is 197 MeV Fermi. In order to make an exponential factor that goes away in about a Fermi or so, you need a mass. The mc squared has to be something like 200 MeV. And that's exactly what Yukawa predicted. He said there'd be a meson with about 200 MeV. And in fact, the pi meson is just about like that. And so it's the so-called meson theory of the strong interaction. And the g, the coupling constant, is basically like the charge. It sort of plays the role analogous to electric charge. So that's it. That's a little longer than I had hoped, but that's the way it goes. We'll see you guys in class. All of space, and it enables these particles to have mass to the degree that they interact with the Higgs field. And we're not going to talk about the Higgs field today at all. I'm hoping that on the third day of this, we'll have a chance to discuss exactly what the Higgs mechanism is and what the Higgs boson actually does. But let's start with the more straightforward and more direct interactions, and those start with the photons. So photons interact with anything that has electric charge. So that could be any of the leptons, any of the quarks. Those are the only things that have electric charge. And basically, the most fundamental interaction is simply an emission or absorption of a photon by an object with charge. So that's all there is to it. Then the weak bosons are the W+, the W-, and the Z, and they interact in a similar fashion to anything with weak charge. So, in fact, it turns out the electric and weak forces have been unified theoretically at high energy. They behave the same at high energy, but there is what you call a symmetry breaking that happens, and at the energies that we see on a day-to-day basis or in our laboratories, they appear to be very different. But in fact, the underlying theory is unified at this point. Welcome back, guys. It's lesson 36. We're coming down to the final stretch. Just a few lessons left. This is the first of a 3-part set of lessons about the standard model of particle physics and quantum field theory. Now, you can't do all of the standard model and quantum field theory in 3 lessons, and maybe I'm foolish to try, but I mostly just wanted to give you guys a sense of what it's about. So that's what we're going to talk about. Let's get started. First of all, there are 2 major families in the standard model. There's the sort of matter part, which consists of the fermions, which is, and there are 2 groups of fermions, the quarks, up and down, charm and strange, and top and bottom. They come in pairs. Each pair has a positive and negative member. The positive is plus 2/3 charge, the negative is minus 1/3 charge. And notice that the positive charges are 1 elementary charge greater in charge than the negative charges. So the difference in charge between up and down is 1. And that's also true of the leptons. The leptons have a difference in charge of 1, but in this case, the electron has a negative charge. The neutrino, the electron neutrino, has a 0 charge, and so they have a difference in charge of 1 unit. Same with the muon and the muon neutrino, and the tau and the tau neutrino. So the leptons are relatively light particles with nearly massless partner particles. The electron has much, much greater mass than the electron neutrino. But having said that, the up and down quarks are even more massive than the leptons. Then the leptons in the same column, I should say. And then there are the bosons. The bosons generally play the role of the force carriers that act between the leptons. I say generally because there are exceptions to that, but we got the gluons. The gluons, it turns out, carry the color force. In other words, quarks have a color charge, and the gluons are the ones that the quarks exchange with one another in order to interact via the color force. And the anything with charge and weak charge can interact using photons, which are the gammas, and then the W and Z bosons are the carriers of the weak force, and they interact with objects that have weak charge. And finally, I don't want to call the Higgs a force exactly. The Higgs is basically a field that is theoretically permeates all. Then there are the gluons, which interact with quarks. So quarks carry color, and the gluons, in the same way that the photon interacts with the electric charge, the gluons interact with the color charge. And the other thing is the gluons actually carry color with them, and so unlike photons, gluons can interact with one another, and that's one of the things that makes dealing with the quarks and the gluons and the color force in general so complicated. Now, where can you go to learn more? There is a free book on the internet. You can go and grab it from the Particle Data Group, and it has all kinds of lovely details about all the wonderful stuff that you can learn about the standard model and how it all goes. I just want to point out a couple things. This is a free download, so it's an amazing resource. One is that we're going to be working with the baryons a lot right away, and I just want to point out also that these guys have a whole chapter set aside for Monte Carlo techniques, so I'm not making this stuff up. People really use this to get work done, and so as I'm encouraging you to use Monte Carlo techniques in your computing projects, understand that it's a skill that may prove useful in the future. Okay, so let's get back to those baryons.
QuantumLaserPointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves. When the peaks of two waves overlap, it creates a band of light. When the peak of one wave meets the valley of another, light is canceled out. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. It's been called the granddaddy of all quantum weirdness. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers. QuantumLaserPointers.com.